an overview of fluids, which is one of the 5 topics that's going to be on your AP Physics 2 exam. So what I'm doing is I'm looking at the 5 steps to a 5. For those of you who have this book at home, great. I know there's a couple people who weren't there the last day or two, and so that's why I ended up going into school and scanning these in. And so I apologize for that. I had literally had to cut them out of a book. And so they're kind of crooked because they weren't 8.5 by 11. So big ideas from this. And I do think this is a pretty good chapter for sure. This goes along with your textbook chapter 13, a little bit of stuff in chapter 12. So big ideas. Make this a little bit bigger. Essentially, static fluids, pressure at any point is caused by the weight of the column of fluid above it. So basically, that's going to be, and fluids can be gases or liquids. So for example, if you're at the surface of a liquid, that's just the atmospheric pressure, and that's about 100,000 pascals. Now, the pressure, the density of the atmosphere changes at different elevations, so we normally will take that as being 100,000 pascals at sea level. If you go below the water surface, or the liquid surface rather, if you want to find absolute pressure, you'd add that 100,000 pascals in, plus rho, which is density, times G times H, which is basically the pressure caused by the column of liquid. And now here they're talking about absolute pressure and gauge pressure. Archimedes' principle is a big idea, so that the buoyant force is based on the weight of the fluid displaced. That's key, not the object itself, but the weight and the density of the fluid displaced. Pascal's principle essentially says any increase in pressure on the surface of a fluid increases the pressure at all points of the fluid by that same amount. So the idea, for example, is like when we did that lab with the syringes, we had an atmospheric pressure inside and outside the syringe to start with. And then when we added the scale on top and then we pushed on that, that additional pressure also was on the inside. And then for fluids that are in motion, we want to be able to use Bernoulli's equation. We want to be able to use the continuity equation. So that's basically A1 times V1 equals A2 times V2, area, cross-sectional area times velocity. Bernoulli's equation is complicated, but applying it is not always that complicated. So here's these relevant equations. I'll shrink that down again. If you notice, these are on your AP2 formula sheet, all in one spot. This is the version that I've given you. Hey, since you're going to be taking the test at home, you may want to use this version with these labeled formulas on it. I'm not sure what the requirements are going to be yet. AP is going to release more information on April 3rd. So this is electricity, magnetism, and mechanics. These are fluids and thermal physics. So, and I've separated these into what I consider the thermodynamics ones, T1 through T5, and the fluids ones, F1 through F6. This whole thing is F6. That's the Bernoulli's equation. In fact, let me see if I can do this here. See if I can surround that whole thing. Oh, God, that's a friggin' fat line. That's pretty good. Oh, geez. Never mind. Okay. But anyhow, those are the same ones that are talked about right here. So, big idea is, why the heck do you get pressure at all? Well, it's because of molecules hitting things. So in the area of thermodynamics, they'll talk about that a little more, is that the population of molecules at a given temperature are going at different speeds. So there's a whole range of speeds. And I think I drew a curve that looked like, sadly, it's a lot like these curves for this COVID case, right? It's these up and down curves. So the population of molecules at a given temperature is going different speeds and in different directions. But on average, they have a certain average speed and average kinetic energy. So we'll talk about that a little bit more with thermodynamics. But the idea of the pressure is, here, on average, when molecules hit a wall, the parallel components all hit randomly, so they kind of cancel out. But when they hit a wall, basically they rebound back in, and so there's an impulse back in, and therefore this molecule also applies an impulse to the wall. So that's Newton's third law in a way, equal and opposite forces, and that creates a pressure. So you do want to understand that the pressure is caused by the motion of molecules. Due to gravity, we've got something else. It's basically due to the weight of the atmosphere or liquid above things. And again, you can see how crooked these pages are. Sorry. Density, rho equals mass over volume. So that's something that you would need to understand how to rearrange to solve for mass or volume or things like that. So basically, the standard units for that are kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. It's probably something useful to have. So at a particular one way you could think about the mass of an object or of a liquid is mg, right, is the weight of the liquid. The weight of a fluid, rho vg. Why? Because rho times v is equal to the mass, and that's just a rearrangement of the density formula. General pressure equation, since pressure is measured in pascals, which is newtons per square meter, force over area. There's actually an interesting application later in this chapter about that. And it talks here about atmospheric pressure. So this is kind of an interesting thing. Basically, what you want to think about is the pressure at a given depth, again, is caused by, say, pressure of the atmosphere above plus the weight of the water, pressure caused by the weight of the water column. So that's density times G times H. And this is for static fluids. And the pressure is only based on the height and the density of the liquid, along with if you add an atmospheric pressure. So notice the shapes don't matter. It doesn't matter if you have a large, wide area or a narrow area. The pressure at the bottom here would be the same for all four of those cases. Same way here. If you're at the same depth, the pressure would be the same. This is a good example of a problem. It's asking you to figure out if you had like a deep diving submarine somewhere down here, it had a window of 20 centimeters diameter, what would be the force of the water on the window? They also could ask you what's the net force if you know the pressure inside is, say, at 1 atmosphere or something like that. So we have to be a little bit careful. If they asked you the net force and the pressure inside the sub was 1 atmosphere, then you just wouldn't have to take into account that atmospheric pressure on the outside, because it'd be both caused by the atmosphere outside and inside the sub. Here they're only asking about the force of the water on the window, so that would be only the outside pressure pushing in my mind. And they go through the calculations here to solve for that. So this thing should be a little bit odd to you, and you should say, hey, wait a second, how can that happen if the pressure at any depth is the same? Well, the way it could happen is either A, it can't happen if this is all one liquid, or it could happen under two other cases. One would be the atmosphere up here is not actually open to the atmosphere, but it's a pressurized container, and you can figure out how much extra pressure there is by how much extra depth there is on this side. The other thing could be the liquids are not the same on this side as on this side. So therefore, that would mean at this depth at the bottom, the pressure would be the same caused by this liquid and by this liquid. If that's true, which liquid do you think would have a greater density? Dun 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 dun. Hopefully you recognize this would have a greater density because the pressure would be caused by less depth, less H, I guess, in that equation, but by a greater density. So the rho GD would equal the same on this side as this side. And they're talking about that here. I think this is a similar example one we had in our textbook where you had mercury on one side, water on another. It was kind of a pain in the butt. Not a bad idea to go through and solve something like this. I don't think the AP will ask you for a response that's that mathematical, but I think they will ask you to show a strong conceptual understanding. So if you saw a case like this, you would need to be able to explain possible reasons why. Here's a pretty cool example. It's about a hydraulic jack, and it's saying that on this side here, you've got only 1/100th of a square meter. On this side here, you've got 0.2 square meters. It's asking you if the player has a weight of 1,500 newtons, which is about 300 kilograms, which is a lineman, 300 pounds rather. 300 kilograms would be ridiculous. At any rate, what force would you need to apply over here to keep this piston at the same height? Well, basically you need the same pressure on this side as this side. Pressure is force divided by area. So in this particular case, since there's a lot less area, we would need a lot less force. And notice they're showing those being equal to each other. So it's actually only 75 newtons of force on this side. So it's about 5 pounds, a little over 5 pounds, I think, per newton, or 5 newtons per pound, rather. So that's like about 15 pounds of force, which is pretty amazing. Well, that should make sense, duh, because if this is 20 times the weight over here, 20 times the area over here is here, should be 20 times the force over here is here. So 300 pounds divided by 20 gets me 15 pounds. So duh, I guess I should have known that. Now the other interesting thing is they don't talk about this here, but this actually can tell you something about conservation of energy. So let's say that you wanted to cause this as like a hydraulic lift. So let's say a car was sitting on here or something like that. You want to lift it up. Well, in this case, this is a smaller area, so in a smaller force. So if we push this force down by 1 meter, force times distance is work. So let's say 15 newtons times 1 meter is 15 joules of work. Here, this is 300 pounds of force. Well, it's not like it's going to move up 1 meter, partly because this area is 20 times as big. So for the same volume that you're squooshing down over here, to have the same volume coming up over here, with 20 times the area, you would only go up 1/20th the height. So 1/20th of a meter multiplied by 300 pounds, or however many, 1,500 newtons, means you would get the same work output over here as you put in over here. I think that's really interesting. And it shows a case of mechanical advantage where you can apply a lot less force over more distance and get this thing to move. I mean, you couldn't push 300 pounds probably on your own, and certainly a hydraulic jack for a car couldn't do that, but automobile shops do use something like this to lift up cars, and basically they have a large area over here that's pushing up a car, a small area where the force is being applied down. So pretty cool. The barometer over here, looks like someone's giving you the finger. That's kind of mean, but it's just a tool. I'll let you read through that. I'm not sure I like this diagram. First of all, why does this say downward pressure when there's an arrow up and upward pressure when there's an arrow down? I think they flipped those. So that's a little bit annoying. The rest of things are okay. I think this is a little bit complicated in terms of understanding why things float. I think it's easier to think of it as basically that the density of the object is less than the density of the liquid it's immersed in. So if something is floating, it has zero net force on it, which means the gravity down is equal to the buoyant force up. So if a body is submersed fully or partially, the fluid exerts an upward force equal to the weight of the displaced fluid. That's rho of the fluid, V of the fluid times G. I think this is an easier way to think about it. Now, you want to be careful to use the density and volume of the fluid, not the object itself. Now, you might need information about the object's density and mass to figure out the object's volume, but it's the density of the liquid that's displaced and the volume of the liquid that's displaced that tell you the buoyant force. But if you know something's floating, that would obviously equal the object's weight. And a common mistake is assume that the volume is equal to the volume of the displaced fluid. Well, again, if an object's floating, its volume is going to be greater than the volume of the fluid it displaces. And I already talked about Newton's third law. This is a good example. I think we did some things like this on a quiz we had, so I would look over this example. This one is the continuity equation. It's the volume flow rate. So I think with this equation sheet, it's this F5 formula over here. So Basically, the cubic meters per second in a closed system can't be different here than here than here. So that's got to be the same everywhere. That can allow you to figure out a velocity at different points. Remember again, to get the cross-sectional area, if you have to calculate it, it's pi r squared, but many times you can use proportions. So for example, if this diameter is 1/4 of this diameter, if you think about pi r squared, that means the area here is 1/16 the area here. Okay, and that means that the flow rate here would be 16 times as much as that here to have the same amount of mass and volume flowing per unit time. The other thing to think about is we're going to have high and low pressure. So fast flowing fluids have low pressure, slow flowing fluids have high pressure. Here's a good way to think about that. If you look at this, here you're going fast and here you're going slower. I wish the arrow was shorter here. Then what's happening? Well, you're having an acceleration pointing to the left over here. I'm going to flip that direction around. So you have an acceleration that's pointing the opposite way of the direction of the fluid. What that means is there's a net force pointing that way. So you have to have, since pressure is force divided by area, if you have an acceleration pointing that way, that means you have to have a greater net force per unit area over here than over here. If we go from the fluid was flowing to the left, we'd have to speed up. That would mean the acceleration would also have to point to the left. So remember, an acceleration can both speed something up and slow something down, depending on whether the acceleration is in the direction of motion or opposite the direction of motion. So this is Bernoulli's equation. Looks pretty complicated. It really deals with an application of conservation of energy, and they talk about that right here. You've got gravitational potential energy on each side. If the height changes, you've got kinetic energy on each side. If the velocity changes, and you've got pressure on each side. So they talk about trying to remember that, but you get a formula sheet. So the only thing I think is a little bit tricky is many times you have a lot of free information here, or you could get free information. For example, these velocities you could get if you know the different cross-sectional areas and say one of the velocities. But again, I don't see in a 45-minute AP exam they're going to have a lot of time for you to do things like that, but they may ask you to conceptually understand what's going on, which is why you want to make sure you can think proportionally and with variables. This is kind of a neat little demo here. If you hang two pieces of paper and parallel to each other, so hang them down and you blow in between them, the pieces of paper will actually come together. Now I think they're showing the airspeed is going up from the bottom here, but it's easier if you hang down and blow down from the top probably. So basically fast airspeed, lower pressure. And they say generally, I assume on the AP exam that's going to be pretty universal. I like how they're talking about someone with strong lungs when we have a respiratory pandemic, but not timely. They didn't know that was going to happen. And they do talk about someone with strong lungs like a trombone player, trumpet player, things like that. So this would be kind of cool to do. Here, I think they again messed up here. Well, they didn't really mess up. They say P1 equals P1. That's because it's open to the atmosphere and these are the same. I guess you could put P2 over here and just say somewhere else that P1 is equal to P2. So I guess that's the idea. They also talk about some applications here, which I think is useful. And again, go through this. Kind of a nice example. One of the ways that airplanes create lift is through the Bernoulli effect in the shape of a wing. Another way is angle of attack. So if the wing was pointing like this at an angle, then the air would hit it and that would cause lift also, because the pressure would be on the bottom side of the wing. But for level flight, something like this causes the lift. Also, baseball, basketball, something like that allow things to move differently. And the Magnus effect is one of the examples related to the Bernoulli effect as well. And I'm going to show a cool video of that from Veritasium. But all of these are nice practical examples I think they could ask about. And the end of the chapter also shows some sample practice problems, and at the end they also show answers and explain those. So that's a pretty good idea to do that. So they talk about the reason. Anyhow, hopefully this helped as a review for fluids.